Oh, hey everyone. So we finished our discussions of the laws of thermodynamics, at least for right now. We might every once in a while come back to some of the ideas for thermodynamics, but now we're going to start talking about the other topic which is going to occupy our attention for the rest of the semester, and that has to do with electrodynamics, electricity and magnetism. And the laws of electricity and magnetism are very, very interesting. They're very fun, and there's a whole lot of very interesting things that we get to talk about, but they are new, and the best way of writing them is in terms of certain equations written using vector calculus. And I've got these equations written right here, and you're not supposed to know what these things mean right now. The rest of the semester is a build-up to get all of these equations. But these equations, the four up top here with the E's and the B's, these are what are called Maxwell's equations, and they are the complete laws of electricity and magnetism. Okay? Everything that we know about electricity and magnetism, and in fact more than that, is hidden in these four equations. Okay? The next equation underneath that with the F, this is the force on some electric charge which is moving through these electric and magnetic fields. And then finally, the last two are writing the electric and magnetic fields in terms of other things, okay? What are called potentials, vector and scalar potentials. So the rest of the semester is going to be done trying to understand these things, trying to build up these equations, and really build up an understanding of them. And many times when you sort of learn the laws of electricity and magnetism, you start off with equations which are wrong, or better yet, incomplete. Everybody always starts with Coulomb's law, and we'll talk about Coulomb's law and so on. But Coulomb's law is not always true, and it's very easy to kind of get it in your head that these laws are always true and always go back to these laws and so on, and that doesn't work. Better, I think, is to start with the complete laws of electricity and magnetism, which are written right here, and work out the different cases of these things. Okay, start by working out the simplest cases when things are standing still, when nothing is varying with time, and so on. Then the equations are very simple. But I think it's important to make sure that you understand that that's only a special case. And so I don't want to do it by starting off with Coulomb's law on page 1, the way it's usually done in the textbook. I want to start with the exact laws of electricity and magnetism and then work out the simple cases. But in order to do that, I do have to write down the equations using these ideas of vector calculus. Both the differential form, which we'll talk about now, and then also the integral form, which will be the basis for the next lecture. And so there's a nice relationship between the integral and differential forms, and it's possible to switch back and forth at will. And so again, that's what these first two lectures are going to be about. So I want to do a couple more of these mathematical lectures, as we've had before, where the whole idea is just to teach you something about the math. Just to do something where basically I'm doing all of your Calculus 3 in 2 lectures. Okay? And it's possible to do this because most of the time when we're going to be working out these equations of vector calculus, we're going to take sort of simple situations where it's not complicated, where there's lots of symmetry. And I'll really define what I mean by symmetry later on. But we're going to work out sort of simple situations, which it is possible to actually work out some things without getting into too many mathematical nasty details. Okay, so that's what I want to do. So today I want to start off by talking about vector calculus, specifically the differential vector calculus. I want to talk about partial derivatives. I want to talk about gradients, differentials, curls, divergences. Okay? And then I want to tell you about what these Maxwell equations actually mean. How do we interpret them? How do we think about them? Okay? Next time we'll talk about the integral forms of vector calculus, the gradient theorem, the divergence theorem, Stokes' theorem, Gauss's theorem, things like that. Okay? So again, a couple of nice mathematical things. Some of this will be familiar to you, especially if you've had Calculus 3 already. Some of it might be new. Maybe you've seen partial derivatives in your 101 class. Okay, I often cover those things. That's something you might see. Okay? But some of this might be new. And so some of this, it's good, even if you know this, it's good to go over it again. All right? Incidentally, a lot of what we're going to be talking about for electricity and magnetism may not be in the book. Okay? These differential forms are sometimes mentioned in the textbook, sometimes not. The integral forms will be in the book. A good resource for this stuff. In fact, these two chapters here, these two lectures, are in the Feynman lectures on physics, and I've linked to those in the modules and so on. But I recommend, actually, if you really want to start understanding this thing, start reading volume 2 of the Feynman lectures on physics. Just start at the beginning, okay? And that's really a great way of learning this stuff, because the laws of electricity and magnetism, they are new, and they take a little getting used to. Okay? There are some things, some intuitions that you have, say from gravity, in fact, that you can lean on, and also the ideas of potential energy and so on, that you can use to get a good feeling for electricity and magnetism. But again, it's sort of new ideas, and we got to work up to that. Okay? So I really do recommend reading the Feynman lectures on physics, okay? All the time, but specifically start looking through volume 2. All right. So here we go. So vector calculus. Now, we're going to be dealing with vectors. And the thing about vectors is how the vectors come about depends on your choice of coordinate systems. You can write down a vector, and we always sort of learn what a vector is. It's this sort of arrow with a length. And that's really a good way of actually thinking about it. If you go on to slightly more fancy things, like we do discuss in Physics 103, you learn that a vector is something that transforms a certain way under a coordinate transformation. And that sounds scary, that sounds fancy, but all it means is if you go to some new choice of coordinate systems, then the components of your vector, they all kind of change into one another. If you turn your head and look at a vector from a sideways point of view, then the components of that vector all rotate into each other from this new rotated point of view. And that's really how you define a vector. And that's a more fancy way. Again, something that we talk about in Physics 103, but we won't really need here. Actually, if you go on to an even more fancy version, you learn that a vector is an arrow pointing in a certain direction with a certain length. Okay? And so you kind of come back on itself like that. Okay? But we do have to start thinking about different kinds of coordinate systems, okay? Different choices of coordinates, because in some cases, it might be nice to, say, use Cartesian coordinates. And Cartesian coordinates are the things that you're very familiar with, okay? We can express a vector in terms of its Cartesian coordinates. And so you can pick a point, and you can specify that point in terms of how far you move along the x direction, how far you move along the y direction, how far you move along the z direction, okay? In particular, a vector, okay? A vector, I don't call it F or something like that. This is not necessarily force, it just stands for some vector. Why not V? I don't know, just F. F sounds good. Okay? Any vector F can be expressed in terms of its different components. The F sub x component, I hat, plus F sub y component, j hat, plus F sub z, k hat. Okay? And this would be a nice way of thinking about the components of a vector. How far you move along one direction, plus how far you move along another direction, plus a third mutually perpendicular direction. Okay? And incidentally, just as an interesting thing, if you have your vector and you want the x component, you know that you can just dot that vector into the I hat direction, for instance. Okay? Whatever direction you want, you just take the dot product of the unit vector with that total vector, and that gives you the components along that direction, for instance. Okay? And so very nice, very simple things. Things that you have talked about before. And so, of course, you know examples of vectors, velocity, position, and so on. Okay? Position, for instance, that's an important one. Okay? The position vector. In this case, that's just r. R is your position vector. And this is just x I hat plus y j hat plus z k hat. How far you move along x plus how far you move along y plus how far you move along z. And so if you look at this Cartesian graph here, then r is just that thing. Okay? In addition, we've got another nice thing here, which is called the unit vector. Again, a very, very important vector here, which I'll write as r hat, and that's just defined as the vector for the position. Okay, this is specifically the position unit vector. And this is defined as the vector here divided by the magnitude, where the magnitude of the vector is square root x squared plus y squared plus z squared. It's given by the Pythagorean theorem, three-dimensional Pythagorean theorem. Okay? And so in the Cartesian coordinates, the unit vector, okay, again, the position unit vector, r hat, which is r over magnitude r, you can write as x I hat plus yj hat plus z k hat all over square root x squared plus y squared plus z squared. And this completely specifies the position unit vector in terms of its x, y, and z components. And how do you picture that? Okay, well, it's very, very simple. If this is your x direction, that's your y direction. And this is your z direction. And if your r vector, let me just change up colors here. If your radial vector here, your position vector stretches out there, then r hat is just a little tiny unit vector that points in the same direction as r, but it's only 1 unit long. In other words, what I mean by a unit vector is that r hat dot r hat is equal to 1. Because r dot r is equal to r squared, where this is your dot product. Again, things you learned in Physics 101 and so on. And a very, very nice situation where you'll talk about this position unit vector is Newton's law of gravity. So if you got some mass m here and you got another mass over here, little m, separated by some distance r, then the gravitational force between those things is minus gn m over r squared r hat. Okay? Where r hat, again, is the little unit vector that points from one to the next. And the minus sign here on Newton's law of gravity is telling you that this is an attractive force. Okay? Incidentally, you can express the r squared in terms of the x squared, y squared, and z squared. Okay? And so this is a nice way of thinking about these things. Of course, you can always define any unit vector. Okay? A hat, for instance, as just the vector a over the magnitude of a. Okay? That's a definition. So again, things you talked about in Physics 101, so we don't need to really think about them. But it does turn out that there are certain situations in which Cartesian coordinates are not the best thing to work with. You might have a situation in which you got a rectangular box. Yeah, then in that case, it does seem like the Cartesian coordinates would be best. Okay? Cartesian coordinates are very nice because, for instance, the unit vectors along the x, y, and z direction, I, j, and k here, okay? The unit vectors along those directions, they're all constant. Okay? They don't change. There's no derivatives when you think about the unit vectors. Okay? I dot, or dot is the derivative with respect to time, would be equal to 0. Okay? So there's lots and lots of benefits to working out the Cartesian coordinates and vectors in terms of those Cartesian coordinates, but it's not always the most convenient one for calculations. There might be other situations in which you might want to use a different set of coordinates. Okay? Another one, which you may not be too familiar with, is actually cylindrical coordinates. Okay? And cylindrical coordinates is very nice if you're working, say, with wires or something like that, something with a cylindrical symmetry. So if you have, for instance, a long cylindrical wire, let's say, okay, and wires are very important when we talk about electric currents, electricity flowing along these wires, and in fact magnetic fields. Okay? Magnetic fields turns out to be very important in wires when there's currents moving through them. Then this is a very nice way of thinking about sort of things. You can talk, instead of doing your Cartesian coordinates here, okay, this is your Cartesian coordinates, we can instead say, well, how far, okay, you pick some origin here, okay? Here's your x, here's your y, and here's your z, okay? You can define this in a different way. Okay? Suppose that you want to pick some spot, say here, right here, say on this wire. You can give it in terms of the x, y, and z components, or you can say, well, this thing here has got a certain, no, let me not do it that way. Okay? It's got a certain radial distance, It's got a certain radial distance here, okay, from the center. There's a certain distance here, r, okay, that we come off of here. Let me maybe draw it a little bit bigger. Go away. So just to keep consistent with the colors, here's my thing here. Okay. The green looks like this. Okay. Here's my x, here's my y, and here's my z. So I pick some spot right here. Again, there's a certain radius. In fact, let me take it right here. okay, on that spot. So there's a certain radius, r here, that I come off of the z-axis. Okay, that's my radius. In addition, this thing here has got a certain angle that it makes in the xy axis. Okay, how far am I along the surface of this cylinder? And then finally, there's also a z direction. So I can specify this point by either saying x, y, and z components, or I can say r, phi, okay, where phi is this xy plane angle, and then z. Okay, so this kind of blends together a little bit of the idea of polar coordinates plus Cartesian coordinates. So that's really a nice way of thinking about it. Polar coordinates, like we've talked about for 101, plus Cartesian, okay, along z, okay, along the z direction. And so that's a nice thing. Okay? That's a nice way of expressing these things. Okay? Now, when you do this, when you switch from Cartesian to cylindrical, okay, well, now you can't express your vectors in terms of the same x, y, and z components, in terms of the same I, j, and k unit vectors. We got to come up with a new way of thinking about these. So vectors in cylindrical. Okay. So you got a vector. Okay. Now, here's the thing. The vector itself, this geometric quantity, okay, so let me write it. Let me draw this thing. Here's your x, y, and z axes. Okay? And let me draw a vector. So here's your vector. Here's your vector. Here's your vector, let's say f. Okay? And again, in Cartesian coordinates, then I can write this vector f as some f sub x, x component plus f sub y, j hat, plus f sub z, k hat. Okay? How much this thing stretches along the x direction, how much along the y, and how much along the z. Okay? And I express it in terms of these I, j, and k unit vectors. Incidentally, sometimes you'll see this written as f sub x, x hat, plus f sub y, y hat, plus f sub z, z hat. It's the same thing. Whichever form you like to use, go ahead. It doesn't make any difference. Okay? And so, these are what you get in Cartesian coordinates. Now, suppose you want to choose to use a different set of coordinates for these things. You want to use the cylindrical coordinates. Well, in that case, you don't have the same vectors. You need vectors that sort of point in certain directions here. Okay? You need vectors. How do I get the x component? How do I get the I component? Well, the I component is the thing that changes along the x direction, keeping the other two directions fixed. So I also need something like that for my cylindrical coordinates. I need something that points, if I picture this little f here, and let me just write it down here. Okay. So this is my f. If I picture this, okay, I need to specify this thing in terms of a new sort of triplet of unit vectors. I want to keep this k hat, that I like. Okay. How far does this vector stretch along the k direction? The other thing I want to do is this radial direction, r hat. Now, this is a 2D r hat. Okay? Some people use rho or something like that. So you got to be careful about what r you're talking about. This r hat here for cylindrical coordinates is not the same as this one here. This is a 3-dimensional thing. This r hat here is the purely radial sort of direction. Okay? I'm sorry, it's the purely sort of direction coming off of the z direction. This r here only depends on sort of x and y. Okay? Then in addition, there's another one here about how far this thing points along the phi direction. Okay? So if you picture sort of the projection of this vector down into the xy plane, basically imagine there's a light up here and it's shining down and it casts a shadow. Okay? This vector casts a shadow. The angle that shadow makes, that's the projection. Okay? Well, that'll be your phi hat. And the phi hat actually points into the board. And so you got this triplet of things here, okay, which I might draw sort of like this. Okay, a z hat, the k hat piece points this way, your r hat points this way, and then your phi hat points in that direction. And these things are all at right angles to each other. Okay, so this is your set of unit vectors. You got r hat, phi hat, and z hat, k hat. But the thing is, I, j, and k, your Cartesian unit vectors, those don't move around. But your r, phi, those pieces do move around. These things change. If your f points down here, for instance, well, look, now your r points in this direction. Your phi points in some other direction. Okay? The z still points in the same direction. But the r and phi, these change depending on where you move. All right? And so this thing is going to be a little bit different. All right? So you do have to worry about those things. So for instance, if you take the derivative of this vector with respect to time, because something is moving around, then you will have an r hat and a phi hat dot. Okay, so you do got to be a little careful. We won't do too much with that, but again, it's something to be careful of. Now here's the thing. This vector f, it's the same vector here as it is there. It's that same arrow in space. And however you choose to define it, however you choose to write it, whether it's in Cartesian coordinates or cylindrical coordinates, that's up to you. Okay? The vector itself is a geometric thing and does not change depending on how you choose to define it. What does change, though, is the vector components. The components are going to be different. Now, you're going to have some f sub r, r hat, the piece that points along this direction, plus some f sub phi, phi hat, plus this guy doesn't change, f sub z, k hat. Okay? In this case, these things don't change. Okay? And so, it looks a little more complicated, okay? But it's the same sort of idea. And we're going to see examples of these kinds of things in a little bit. Right now, I'm just sort of defining these things. And again, this may be familiar to you from Calculus 3. I hope so. Okay? I hope this is not the first time you're seeing these sorts of things. All right? So, this is cylindrical coordinates. Again, cylindrical coordinates are very, very nice if you got things like wires or something like that. Or if you got a situation in which everything is the same as you move along the z direction. If nothing changes along the z direction, but only depends on how far away you move from something, then it's a good choice of coordinates. Okay? Another one, which we'll use even more, spherical coordinates. Okay? Oh, sorry. One thing I wanted to show you about this. Suppose that you want to go back and forth between the Cartesian and cylindrical coordinates. Okay? Well, that's actually very, very easy. This is something you already know how to do, because you studied Physics 101, okay, x, y, and z. Again, here's a point, P of x, y, and z. And it's also the same point, P of r, phi, and z. If you want to go between these things, okay, for instance, then you know, well, the z is the same. Z doesn't change. Z is just the projection of this vector, okay, of this point. Okay, and again, here's your f here. Okay. Actually, let's just take the position vector just to make it easy. Okay, so say it's your position vector. And you want to express the position vector in these two different sorts of coordinates, or figure out the relationship between these two things. Okay, well, that's easy. That's not so bad. Okay, this projection down here, so this distance here, we'll call, I guess maybe not use the position vector. This is our f. This distance here, that's r. Okay. This radial distance here is r. And then this angle here that it makes, again, that's phi. Okay. Well, the length of this thing up here is the same as the length of this. This is r. And so if you're looking for your x component here, well, your x is just r cosine phi. Okay, it's just this adjacent side. And then your y, obviously, is r sine phi. And then your z is just z. Okay, these things don't change in this case. And so you can do this. Or you can go the opposite direction. You can say that r is square root x squared plus y squared, and that phi is the arc tangent of y over x. Okay, so these things here, these are your coordinate transformations. Okay, which is a fancy way of saying, well, how do I switch from polar to Cartesian coordinates and back and vice versa? Okay? So nice. Nothing to it. Okay? Nothing to it. All right, so again, that's cylindrical coordinates. Okay, very useful for things. Another thing that we can talk about, okay, it's something even more useful, is going to be spherical coordinates. So in this situation here, this is very nice if something has what's called a spherical symmetry. If you got a ball, for instance, you can take it and twist it and turn around. It always looks the same. So in that situation, nothing about that ball can depend on the angles that you hold it at. Because if it always looks the same, no matter how you twist and turn it, it can't depend on angle. Things can only maybe depend on how far away you go. So I'm going to introduce the same sort of idea, this spherical coordinate system, okay, in exactly the same way. And I'm going to define my point here, P of r, theta, and phi, in terms of the radial distance away I am. Okay, so again, you got to be a little careful now. Now I'm switching from cylindrical, okay, or heck, even just Cartesian, x, y, and z, to spherical. Sometimes called polar spherical or spherical polar coordinates. Okay, so be very careful. This r here, it's written in the same thing. It's not the same as this r. This r is this purely moving along the xy plane distance, whereas this also goes up into the air. So this is our three-dimensional distance here. Okay, so my r here is my square root x squared plus y squared plus z squared here. Okay, whereas here, oops, in this case, r is equal to square root x squared plus y squared in this case. You say, well, do I need the same thing? Well, we're never going to work in two different coordinate systems at the same time. We're going to pick one and stick with it. So it should be clear from the context. Okay? Note, though, that the phi here is the same. Okay? So I'm going to redraw this here. So here's my x, here's my y, here's my z. And again, here's my little point up here. So this point here, I can label as x, y, and z. Or I can say, what's the radial distance I go along? Okay, how long? What's the magnitude of this arrow? What's the angle that this thing makes off of the z-axis? Call that theta. And then again, this same projection, the same idea here, project this thing down, phi. Okay, so I can express in terms of x, y, and z, that set of coordinates, or I can express it r, theta, and phi. Okay. Incidentally, in math classes, the theta and phi are often reversed. I'm not a mathematician, I'm a physics guy, so I'm going to stick with the way that it's usually done in physics and in more applications. Okay, so it's going to be defined this way. The theta is your polar angle coming off of the z-axis, and then the phi is what's called the azimuthal angle. Right? So please don't get them backwards, because that will change all kinds of formulas if you mess up. Okay? So again, in this case here, again, just to redraw my axes here, I got x, I got y, and I got z. And I got some vector here, as before, some vector f, which again I can express as f is some f sub x I hat plus f sub y j hat plus f sub z k hat. Again, I can also define it if I take this, if I zoom in on the point here, instead of talking about my I, j, k as my basis vectors, okay, just to use a word, basis vectors means that any point in my space, in my three-dimensional space, can be found as a linear combination of these things. In other words, to do this, I just express the vector as a bunch of numbers times those unit vectors, and I can get anywhere in my three-dimensional space. Okay, so they span the space, okay, to use some linear algebra terms. If I look at that point, I can also define it. Okay, remember, this is my r, this angle here is my theta. Okay, so r is the distance along here, and then this angle down here is phi. If I look at this point here, so here's the tip of that arrow, that f, I can also express it in terms of three little unit vectors. One that points radially out, r hat, along this direction. So r hat points in that direction. It points from the origin along the direction of f. There's also another one that points this way. This is my theta hat. It moves in the direction of increasing theta. Okay, so it's perpendicular to the z, well, since theta increases in this direction, theta hat also increases in the same direction. And this is my r hat. Then finally, phi hat, because it goes in this direction, the phi hat points into the paper, okay, into the board, into the screen, wherever you're looking at this thing. So this is my set of spherical basis vectors, or base unit vectors. Okay? So in that way, this same vector f can be written as f sub radial part, r hat, plus f sub theta, theta hat, plus f sub phi, phi hat. But again, it's the same exact vector. It's just how do you choose to write it? What sort of components do you use to do it? Okay? Right. Now, in many situations, okay, you might not have all of these things. It might not be pointing along these things. Okay? For instance, it turns out for the position unit vector, okay, if you write this in Cartesian coordinates, okay, then that's r hat is x I hat plus y j hat plus z k hat over square root x squared plus y squared plus z squared. Okay? In terms of spherical, well, that's just r hat. So that's very nice. Okay? In the case of the position vector, okay? In the case of Cartesian, this is r is x I hat plus y j hat plus z k hat. In spherical, r is just r hat. So you can see that there's a very, very nice way of writing these things in many situations. And so it's a lot nicer to have this sort of freedom to choose whichever coordinate system you want to use for a given problem. Right? And so again, most of the time it's pretty obvious what you want to use. If you were doing problems with gravity, for instance, okay, right here, clearly you'd probably want to use spherical coordinates instead of Cartesian coordinates. It's much nicer to write things in terms of r's and r hats instead of in terms of these x, y's, and z's and square roots and all that kind of stuff. And so it's much nicer to do that. Okay? Now, finally, if you want the transformation between the two, okay, well, again, we write down the same thing. Okay, here's my x, here's my y, and here's my z. Okay, here's my point. And so, again, call this r. So, the radius of this thing, okay, well, let's figure out. So, this component along here, that's theta. Well, you see that if the length of this arrow here is r, then z should just be r cosine theta. Nothing to it. That one's easy. Now, this projection down here, okay, where this angle is phi, well, this distance up here is r sine theta. Okay, because, again, the length of this arrow is r, so that's the same as the length of this thing. But the x component here is this side here, which is cosine of phi times this hypotenuse here. And so x should be r sine theta cosine phi. And then y should be r sine theta sine phi. Okay? So it's not so tough to actually work these things out. Just to kind of look at them and see from the geometry. Okay? If you want to go the other way, well, r squared is square root x, r is square root x squared plus y squared plus z squared. Okay? Square all of these things, add them together, you'll see. Okay? In fact, you can practically see it right now. Also, phi is the arctangent of y over x, as it was before, and theta is the arc cosine of z over r, but I got to express it in terms of x, y, and z if I really want to sort of do this right. R, theta, and phi in terms of x, y, and z. Okay? And so these are your coordinate transformations, and if you like, the inverse coordinate transformations to take you back and forth between these things. Okay? So again, these are our coordinate systems. Again, the thing I want to point out is the vector itself. Okay? This f here is the same f, whether you choose to express it in terms of Cartesian coordinates, cylindrical, spherical, hyperbolic, okay, whatever else. There's an infinite number of possible coordinate choices and systems. Whatever system you choose to express it in, it's still the same vector. The components look different, but it's still that same arrow in space. Okay, so now we got coordinate systems. I want to talk about changes. Okay, in particular, I want to talk about derivatives. Okay, so derivatives are very, very simple. You know how to define these things. Okay, the derivative of a function. Okay, that's if you got some function here. Okay, so here's some f of x, and you want to know what's the change, what's the slope of this function at some spot. Okay, what's that derivative right there? Say f prime of x, okay, which is df dx. Okay, how do you define that thing? Well, it's very easy. All you do is you take the positions at two nearby points. Okay, you take the position to find the slope. At a point. Okay, take two very nearby points, okay, and calculate the difference. You calculate the rise. Okay, take f. Okay. Suppose this spot is at x, and this other spot over here is x plus dx, where dx is a little extra bit. So I take this thing at x plus dx, and I subtract away f at x. Okay, that gives me this rise. How much has this thing changed? Okay, so that's my delta f, if you like. And then I divide it by the run, which is x plus dx minus x. In other words, it's dx. And then I take the limit as dx goes to 0. Okay, and this defines my df dx, okay, which is also written as f prime of x. This is my derivative, okay, my ordinary derivative, my total derivative, if you like. Okay, and this is what's called the limit theorem. And again, I really, really hope you know this one. Okay, this is one that you learn in your very first calculus classes. Okay, this is how we define a derivative. But once you've got that, then you can do all kinds of nice things. For instance, just I don't know why I'm doing this, okay, but you should know it. Examples: f of x is x squared. Okay. Well, in this situation here, okay, why am I doing that? Why not? Okay, in this situation, your derivative df dx then becomes again the limit as dx goes to 0. Just to work it out using this limit theorem, x plus dx squared minus x squared all over dx. Okay, that's what I mean by f of x plus dx. Okay, plug in this thing minus x, and so this is the same as the limit. Dx goes to 0. Incidentally, you may have seen this as h or something. It doesn't make any difference. It's all the same stuff. X squared plus 2x dx plus, didn't leave myself enough space. What the heck? Dx squared minus x squared all over dx, which is the same as limit dx goes to 0. The x squareds cancel. 2x plus dx when you divide through by dx. Taking dx this gives you 0, and so this gives you just 2x, which you know it is. And so, of course, you know all these nice little rules, but it follows from these things, okay? In fact, the f of x is x to the n. This follows from this binomial expansion that we've talked about so much, okay? And so, again, I'm tempted to show you, but you can think about it. Okay? I don't want to spend too much time on this. But here's the thing. When we're working out these derivatives, this assumes that you've got only one variable here, that everything can be described in terms of that one thing. But we already know that there's situations in which things can depend on more than one thing. Okay? The laws of thermodynamics, for instance. Pressure might depend on volume and temperature and so on. And so in those situations, it's nice to use more complicated sorts of things to ask, how, for instance, might the internal energy change if you keep the temperature fixed? Well, you know it doesn't, okay? But you change the volume, and vice versa, and so on. Okay, how do those things change? So in those situations, we might ask, how does the function change if you're only looking at part of the change? In other words, it might depend on multiple variables, but you're asking how do things vary when you've got multiple variables? Okay, and so I want to talk about something which, again, may be familiar to you, which is called partial derivatives. Okay, and so partial derivatives are actually very, very, very simple. Okay, if you can do a regular derivative, you can do a partial derivative. There's nothing to it. Okay, here's the idea. Suppose you got a function. Two variables. Okay. We'll start with 2, and then you can obviously generalize it to however many you got. An infinite number in general you could do. Okay. 2 variables. Suppose you've got some f of x and y. And you want to know, well, how does f change? Okay. Well, now you've got to be a little more careful. Does it change because we're changing x? Or does it change because we're changing y? Or does it change because we're changing both? Okay. So I might ask, how does f change if I only change x, okay, but not y? Okay, that's the idea. Okay, so what would the derivative of f be if I changed x but not y? Now, whatever this derivative is, whatever the derivative is when I only take part of the variables, it should give me the same thing as the regular derivative if y wasn't there. So that's something to keep in mind. So I'm going to define this sort of change in f in a certain way. Well, I'm going to say, well, I just want to change f. So I'm going to define the same sort of thing, limit, okay, f of x plus dx and y. So in other words, I don't touch y, minus f of x and y, divided through by dx. And again, take a limit, dx goes to 0. Okay? This is going to be how I define my partial derivative. Okay? The derivative where I'm only taking the derivative with respect to part of the total number of variables that I've got. Okay? This thing here, because I want to write it as a partial derivative, and to tell me that this function here depends on more than one variable, I'm going to write it differently. I'm going to write it as kind of this backwards 6, partial f, with respect to x. That's my partial derivative. Okay? Incidentally, just to mention, some people like to write this as a delta f delta x and say this is, it's not. Please don't write it with the deltas. Deltas are not these d's. They are not these partial derivatives, okay? Delta is not equal to d in general. Sometimes it might be, but don't write it this way, okay? This is something else. This is a partial derivative here. Okay, this is a partial derivative. This is what's called a variational derivative. So don't mix up the symbols. Okay, so that defines how I take my partial derivative with respect to x. And we'll see an example here in just a second. But you might ask, well, what if I change instead y? Well, I think it's clear what you do. Limit dy goes to 0, f of x, y plus dy, minus f of x and y, divided by dy. Okay. And that's going to be defined as partial derivative with respect to y. Okay? Nothing to it. Nothing to it. Okay? And so now you say, well, how do I do this in general? Okay? So suppose you got, okay, as an example, f of x and y is equal to 2, let's say, x squared plus y squared. Just making something up. Okay? This is nice and symmetric. Now, okay, how do I take these derivatives? Well, you can plug them in. You can do all this kind of limit theorem. But you know, for instance, that there's nice ways of getting this. If you have f of x is x to the n, then you know df dx is nx to the n minus 1. So you learn all these rules. Okay? How do you do this here? It's very simple. If you want to take the partial derivative with respect to x, here's what you do. Take the derivative of this function with respect to x in this case, treating everything that's not x as a constant. Not 0, but just treating everything that's not x as a constant and leave it as a constant. Okay? Now, this is not implicit differentiation. Y here does not depend on x. I can walk along the x direction differently than I walk along the y direction. They're not linked. Okay? So in this case, this just becomes 2x. Okay? The partial derivative of f with respect to y, I'm so sorry, it's not 2x, it's 4x. Okay? The partial derivative of f with respect to y, take the derivative of your function with respect to y, treating x, in other words, everything that's not in y, as a constant. This just gives you 4y. Okay? So that was an easy one. Let me take another slightly more complicated one. F of xy is equal to ax squared y cubed, where a is a constant. Okay? Now that's a little bit tougher, but it's still very easy. Same idea. Take the derivative of f with respect to x. That means treat everything that's not x as a constant. So you get 2axy cubed. That's it. That's it. Derivative with respect to y. That would be 3ax squared y cubed. Nothing to it. Okay? Nothing to it whatsoever. And so every time you got these variables, like every time you take these partial derivatives, just take the derivative with respect to part of the variables that you're working with. All right, piece of cake. Okay. Yeah, another example, okay, just for fun. How about this one? A little bit more complicated. F of x, y, and z this time. Okay. This thing here, actually, no, that's all right. A e to the minus a x squared plus y squared plus z squared. Okay, get some really good practice here. A is a constant. Okay, three partial derivatives here because there's three different variables. Partial derivative with respect to x. Okay, I'll go quick. Minus 2ax, a e to the minus a x squared plus y squared plus z squared. Okay, if you like, this is minus 2a x f. Okay, because the f is the same thing. Okay. Partial derivative of f with respect to y, that's going to be minus 2ay times f, and partial f, partial z, it's going to be minus 2azf. Now you notice, in this case, everything is very symmetric, everything is very nice. That's not always the case, obviously. Okay, whoops, and here I did this wrong. That should be squared. Here, you can see you don't get the same answers. It's not sort of nice and symmetric like that. Okay? It depends on what functions you're taking. Some cases it is. Okay? Now, in addition, you can do some additional things. Okay? Now that you got this idea of partial derivatives, and there's nothing to it. Okay? It's hardly worth spending any time on whatsoever. But once you got that, well, what about second derivatives? And higher derivatives? Okay? Well, for a given f of x and y, for instance, and again, you can generalize to higher things. Well, you can take a partial derivative of f with respect to x. You can have a partial derivative of f with respect to y. You can also have partial f, partial y, partial x. And this means take the y derivative of your x derivative. Okay, that's how we define that. But you can also have partial derivative of f with respect to x, y. This is take the x derivative of your y derivative. Okay? So it's the same thing. So you got 4 different possible derivatives. Actually, it turns out there's only 3. Okay? Why? These two things are related. We'll see how in a second. Okay? And so as an example, okay, well, we got some examples back here. My first example, okay, 2x squared plus y squared. Let's work out all the different possible second derivatives. In this case, df dx was 4x, okay, and df dy was 4y. Second derivative of f with respect to x, that's 4. Second derivative of f with respect to y, that's 4. Second derivative of f with respect to yx is the y derivative of this, that's 0. Okay? The y derivative of your x derivative is 0. And your second derivative of f with respect to x dy, the x derivative of your y derivative is also 0. Okay? So it turns out there's a lot of equal things here, but again, that's not always true. Let's see this other case we talked about. Okay, this one's a little bit better. Ax squared y cubed. Again, partial derivative of f with respect to x is 2axy cubed. and partial derivative of f with respect to y is equal to 3ax squared y squared. So working out all the partials, second derivatives. Second derivative gives 2ay cubed. Second derivative of f with respect to y gives 6ax squared y. Notice these two things are not the same in this case. Partial derivative of f with respect to x and y, this is d dx, df, dy. And so that would be 6axy squared. Okay, I'm going a little fast, but you can always pause it and actually take a look at this thing. And second derivative of f, dy dx, that's d dy of df dx, which will be 6axy squared. Okay. Notice, these two things are the same, even though we took a different sort of function here. It turns out, in general, for anything that we're ever going to look at, these two things are always equal to each other for anything we're ever going to look at. Okay? The second order partial derivatives commute with each other. In other words, the order in which you do these things doesn't make any difference. All right? Nothing to it. Okay? Piece of cake. Okay? And you can have higher order derivatives and things like that. Okay? And again, it's easy enough. I don't think I got to spend more time on it. Okay? What else can we talk about? There's another very important thing which we actually have discussed, the idea of differentials. Okay? So you remember in thermodynamics, okay, the first law, it said that the little bit of change in energy came about by dq plus dw. Okay? So in these situations here, you can change your internal energy either by adding or subtracting some heat from it, or by doing some work on it, or letting the work be done. This little du here by itself, this is your differential. Okay? It's a little teeny tiny little delta. Okay, that's it. Okay? Now you also remember that I could write this in terms of, say, entropy. Okay? dq by entropy, dq was dq over t was ds, and dw was minus pdv. So I can write this as tds minus pdv. And so I got some interesting ways I can write these things here, where t is the temperature, p is the pressure, okay, v is the volume, and so on. Okay, we've talked about this. So in general, we can think about a differential of a function. So in fact, this tells me that my du here is du of S and V. Okay? It depends on the entropy and it depends on the volume. You say, what about the T's and P's? Well, sort of. It's kind of a little bit different. Okay? There's sort of an interesting deep relationship between a lot of different sort of thermodynamic properties, which we'll talk about at the very end, the very last lecture on what's called Hamiltonians. But you don't got to worry about that right now. Okay? But differential of a function. Okay? And what the heck? Let me take a function f of x, y, and z. Okay? But you can make it whatever variables you want. It doesn't make any difference. Okay? What is the differential of this? Okay? Well, that'll be just df. Okay? What is that? Well, how can you change f? How can you produce a change in f? Well, you can do it three different ways. Okay? You can change x and treat everything else the same. Okay? And so that change that you get from a little change in x, well, what should it be? It should be proportional to how much you change f when you change x. That's just the partial derivative of f with respect to x. Okay? This is something you've seen before. Okay? If you think about just position. Okay, position. X of t, nice, simple. Okay. X of t is some x initial. Actually, let me even forget that. It starts from the origin. This is just v times t. Okay? Or if you like, okay, for a constant velocity. Okay? Or if you like, dx is equal to v times dt. You wait for a little bit of time, you change your position by just a little bit. But you remember, v here is dx dt. Okay? And so I can write dx as dx dt at some t initial, okay? That's my initial velocity, which is a constant velocity, times dt. So my change in my function, okay, depends on how I change the variable that that function depends on, times how fast that function changes with respect to that variable. So in other words, the derivative of that thing. Now if I go back here, that's exactly what I got right in here. So this is just the change in f with respect to x times the dx. But you say, well, what if I want to change y instead? Well, we can have a df dy times dy. You say, I like z. Okay. And so pick which one is your favorite. You say, well, I like them all. Well, okay. Plus. This would be the total change in your function. So the total change in your function is how fast your function is changing along x times the change in x, how fast it's changing along y times the change in y, how fast it's changing along z times the change in z. Okay? Very, very simple things. Notice we're picking out the same sorts of ideas in this. Okay? So for instance, in the case of thermodynamics, first law here, my du, which is a function of s and v, this is t ds minus p dv. But for a given function, I can always write du is derivative of u with respect to s times ds plus the derivative of u with respect to v times dv. If I compare these things and match them up, then I see that t here is du ds. And p is minus du dv. And so we've got interesting ways of writing these sorts of things. Okay? Interesting ways of thinking about these kinds of functions and so on. Okay? And so that's very nice. Okay? And so my differential, okay, for any kind of function, for any kind of thing that you got, okay, I define my differential. And again, it can be for whatever variables you want to use. Okay? df is just df dx plus df dy dy plus df, partial derivative, df dz dz. Okay? What if instead it's f of r, theta, and phi? Well, then my df goes in exactly the way you expect, df dr times dr plus df d theta times d theta plus df dz, or df d phi, d phi. Okay? Very simple. Now, this is only true as long as the dRs and all these things are extremely tiny, because really you should have higher order terms. Really what this is just the limit theorem. Okay? That's all it really is. Okay? But again, it's more important that you get the sort of idea for this thing. Right? I'm not trying to make it super rigorous. It's sort of physicist level of rigor here, okay? Which is sometimes sloppy, but sometimes not so bad. Right? Right. So with this, we can actually start introducing some interesting things. Okay? I want to talk about something here called the gradient. Now let me look at this differential. Okay? And in particular, let me look at it in Cartesian coordinates. And so I'm going to rewrite again. df is just partial derivative of f with respect to x dx plus partial derivative of f with respect to y dy plus partial derivative of f with respect to z dz. Now, here's the thing. This dx, dy, and dz, this is just a little tiny steps along the x direction, along the y direction, along the z direction. Well, if I sort of think about that and kind of think, well, here's my x, here's my y, and here's my z. Okay? And I step a little distance here along the x direction, so a little dx. Then I step a little distance along the y direction. Then I step a little distance along the z direction. Well, I end up with a little ds. I end up with a little tiny displacement vector. And I'm going to define my ds vector as being a little dx I hat plus dy j hat plus dz k hat. And this is my little bit of displacement along my x, y, and z axes. Okay? And so this is a teeny tiny little displacement vector. Okay? Nothing to it. So if that's the case, we'll kind of look at what I got here. I got in my differential this nice sort of relation. Derivative with respect to x times x. Derivative with respect to y times y, and so on. Okay? This looks a lot to me like a dot product. Okay? You remember a dot product. Suppose you got two vectors. A, which you can write as a sub x, I hat, plus a sub y, j hat, plus a sub z, k hat. Any two vectors you want. B is b sub x, I hat, b sub y, j hat, plus b sub z, k hat. Then the dot product, a dot b, you can write as ax, bx, plus ay, by, plus az, bz. Okay? Doesn't this up here, doesn't this differential look like that? Maybe we can define a vector, okay, with components that look like this. Derivative, okay, of f with respect to x, I hat, plus derivative of f with respect to y, j hat, plus derivative of f with respect to z, k hat. We're going to define a vector like that, okay? And I need something such that that vector dotted into dx I hat plus dy j hat plus dz k hat, okay, gives me df dx plus df dy plus df dz, which is just my df. That's nice. Okay. Now the question is there such a vector that we can define? You say, well, yeah, we can always make a vector by choosing any three numbers and sticking them in there. No, you got to be careful. Again, vectors, the components of vectors have to be related to each other in some way. Okay? For instance, you can't just take, say, the temperature. Well, Boltzmann's constant times the temperature, I hat, plus mc squared j hat, plus some other energy, mgh k hat. These are all energies. These all have the right units. This could be like an energy vector. No, that's not going to work. Okay? Temperature doesn't change into potential energy if you look at it sideways. Okay? So you do have to be careful about these things. However, it does turn out, yes, this does satisfy the correct definition of a vector. And so this thing is a vector, and I'm going to write it this way. Upside down delta. Okay? Not a delta, it's an upside down delta. And this is a certain operation here, such that this upside down delta dotted into ds is defined by that. Okay? And so my df here is just this upside down delta on f dot ds. Okay? And so I define this vector. Okay? And this vector is very, very nice. Okay? And so that's all it is. And so example. Okay? So suppose you've got f of x and y and z, what the heck, is ax y squared z cubed. Right? Then this upside down delta, that's derivative of f with respect to x, I hat, it is a vector. This is something which takes a scalar, okay, this scalar function, and gives you a vector back. Okay? It maps scalars into vectors, if you want to use some fancy math terminology. Okay? So I just take the derivatives. So this becomes a y squared z cubed I hat plus 2axy z cubed j hat plus 3ax y squared z squared k hat. And that's this thing. Okay? And so there's nothing to it. Nothing to it whatsoever. Okay? Piece of cake. Okay? As another example, suppose you got something, here's a useful one, ae to the I kz minus omega t. Okay? A here is a constant, I is square root of minus 1, that's fine. K K and omegas are constants. Let me take this upside down delta. Well, now we've got a derivative with respect to z. There's no x's or y's here, so those are 0. This will be I k a e to the I kz minus omega t times k hat plus something t hat, right? Nope. These are x, y, and z. These are coordinates, okay? These are actual sort of x, y, and z physical distance things. No times for these things here, okay? Are there ever sort of time unit vector t hat things? Yes, but that's when we're talking about relativity in 103, not in here, okay? So no, there is no time thing. That's it, okay? That's all. Okay? So again, we're talking about time and space things here, okay? Okay. Now, okay, some terminology, okay, some names for these things. And we could do more examples, but I think you kind of get the idea. Okay? Names. This is sometimes called del. Okay. So I might say del f, or nabla. Okay, that's another name for it. So if you're doing LaTeX and you want to use this symbol, it's nabla / nabla f. Okay, and so this is the gradient. Now, this is the gradient, and so del f here again, df dx I hat plus df dy j hat plus df dz k hat. Okay, and that's it. Nothing to it. Piece of cake. Okay? And these can actually stand for real, honest directions here. Again, there's no t hat for this thing. Okay, not for anything we're going to do in here. But here's the thing. This is for Cartesian coordinates. Okay. What if you use a different coordinate system? Okay. Well, in that case, it's still the same idea. Suppose you got f of r, phi, and z. So you got cylindrical. Okay. Then you say, oh, well, this is easy, and so on. Well, what's my ds in that case? Okay. Because after all, that's how we define. Well, we're still going to define df as partial derivative of f with respect to r dr plus df d phi plus partial f partial z dz. Now some of this is easy, but we got to look. We got to be a little careful here. This has units of meters. This has units of meters. This has units of not meters. Okay, this has units of radians. We don't get the same sort of thing here. We got to be a little bit more careful. So really, this isn't quite right. Okay? It's not quite right. We got to change it up just a little bit. Okay? I got to think back. I really want my df to be del f dot ds. So what's my ds? Well, ds. Well, so you picture it. Okay? So you go back and think about these things. Here's your x. Here's your y. Here's your z again. Here's your phi. Okay, that's the one that's giving us trouble. Okay? So if you move off in a little direction, suppose you move from here to here. Okay, so you track out some d phi. Well, if this radius here is r, then the actual distance you moved is r d phi. And so you pick up this extra factor of r because you're talking about a real honest distance. So your ds here, let me write it over here because I probably need this space. Okay, so your ds would be dr r hat plus r d phi hat plus a dz k hat. Okay, and so this extra distance here. Okay? Why did I get r d phi? It's the arc length. It's the arc length along that side. Okay? And so that's how much you actually change along there as you move in and out and up and down and so on. Okay? So if I want this thing to be equal to this, then this tells me I've got, again, this is the thing I want it to be equal to. So my gradient has got to have pieces, what? Dotted into. Yes, I'm not leaving myself enough room, sorry. This should be equal to df dr r hat, as exactly you would expect, okay, from the first piece, plus 1 over r df d phi hat, plus df dz k hat, dotted into my ds, dr r hat, plus r d phi hat, plus dz k hat. Then this thing, the r's here cancel, and so I do get back the thing I expect it to be. So it fits with the differential. And so my del f in this case here is more complicated. My gradient is a different sort of thing. Okay? And so the gradient itself is a vector, and I'll tell you how to picture this vector, how to think about what this vector is here in a second. But you have to realize that the vector itself, the components of the vector depend on the coordinate system, just like they do in any other vector. And so the gradient that you write down depends on what it is you're talking about. And so here's the listing of the gradients in some different coordinate systems. We've got the gradient here in Cartesian coordinates. We got it here in cylindrical coordinates. I didn't show it in spherical coordinates, but see if you can figure that out. Okay, how does the vector change as you move along? But actually, I think you can kind of see it. It's not so hard. Okay, and so it does depend on which way you, which coordinate system you want to use. And so most of the time, you just kind of got to look it up. All right. Actually, most of the time, it's not that hard. If something only depends on r, for instance, if you're only looking at a situation in spherical coordinates where things only depend on r, you've only got one term. And most of the time, we'll only have one term. Okay? Every once in a while, I'll have a theta piece that shows up. Usually not so much in the way of phi hats, though. Okay? So, but these are it. And incidentally, all of this stuff, all of these things that I'm going to write down here are going to be in this handy electrodynamics information sheet, which is on the website. So please print that thing out. Have it with you. You can always use it. All right? So that's the gradient. Now, how do I think about what the gradient is? Okay? Well, here's an interesting thing. Okay? Here's the thing. Okay? Remember, again, this differential. We wrote df. I can write it as this del f dot ds. Okay? Now, remember, this is the same as this dot product. So for a dot product, a dot b is equal to ax bx plus ay by plus az bz, as you know. But you also know that there's another way that we can write this dot product. The dot product is also the same as magnitude of A times the magnitude of B times the cosine of the angle between them. And so I then should also be able to write df as magnitude, gradient f, times magnitude of ds times the cosine of the angle between those. Now here's the thing. If I want df to be as big okay, I want the maximum change in my function. Okay? I want df to be as big as possible. Okay? That implies I should choose, well, that implies I want theta equals to 0. So that tells me that gradient f should be perpendicular to ds. And that's how I interpret the gradient of f. The gradient tells me the direction of biggest change. That's how I think about it. The gradient of f, it's a vector. Remember, it's got ij and k components, and that thing here, that vector, tells me the direction I should move in such a way that I change that function f as much as possible. Okay? And so, what does that mean? Well, suppose that you have a situation where you got lines of constant f. Okay? So f is some constant. Maybe all your x, y's, and z's go together. This is 0, this is 1, this is 2. For instance, how do I move in such a way that I change this as rapidly as possible? Okay? Well, I probably don't want to move off to the side like this. That's not going to get me from 0 to 1 as quick as possible. I want to go in as direct a line as I can. I want to move along this in such a way that I'm always moving at right angles. That's my gradient f. Okay? And so I always move in such a way that I'm moving at right angles to the values of these constant f. And so if you're familiar with these topographic maps, which these different contours show you different heights. Okay? This is one height, this is the next height, and so on. Okay? Which way should you go if you want to get to the top of this hill as quickly as possible? Well, clearly you don't want to wander around like this. No, that's not so good. You'd want to go in such a way that you move along in this nice sort of straight path. And you move along in such a way that the lines of your path are always perpendicular to these lines of constant height, of constant f. So here f could represent the height. Okay, that's what the f could represent. So each of these lines is a constant height. And if you want to change your height as much as possible, you move along the direction of the gradient of f. Okay? So that's a nice way of thinking about it. Okay? If you can kind of get these sort of geometric kind of pictures in your head, then some of the sort of vector identities and things like that are very, 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 very simple. Okay? They're very intuitive. Okay, so that's nice. Okay? Now here's something else. Okay? I got this gradient thing here. And this again, df, dx, I hat. Okay, I'll stick with Cartesian, but again, the same thing works here in spherical coordinates, cylindrical coordinates, whatever else. I kind of want to write this in an interesting way. d dx I plus d dy j plus d dz k, all acting on f. Okay? This thing might look a little bit weird, but it's kind of exactly what you think it is. This thing here, in the parentheses, this is an operator. Okay? This whole thing here, this is my del. Okay? My gradient operator is defined to be, at least in, again, Cartesian coordinates. It would be different in the other coordinates, but you see how to change it. Okay? d dx I hat plus d dy j hat plus d dz k hat. This is the gradient operator. And so this thing by itself, what do I mean by operator? It doesn't do anything until you give it something to operate on, some function of x, y, and z. And then when you operate on that function with this operator, it gives you back the gradient of that thing. So this is nice. Okay? If this thing actually works, then what that means is we got a brand new vector here. And with a vector, there's all kinds of nice things that we can do with a vector. Okay? So it does turn out, and again, the proof of this goes with transformation properties and so on. It's discussed in the Feynman lectures. I don't think it's worth spending time on it now. Okay? But this gradient, okay, is a vector. Okay? Specifically, it's a vector operator. Okay? And again, until you give it something to operate it on, it's incomplete. It's just a bunch of partial derivatives of things, but you can't actually calculate anything until you give it some function to actually operate on. Okay? So because this is a vector, treat it like a vector. Okay? If you think about a vector, what's some things you can do with a vector? Okay? Well, one thing you can do with a vector, suppose you got a vector f here. Okay? One thing you can do is multiply by a scalar. multiply by a scalar. Suppose you got some alpha here. Okay? You can create a new vector. Okay? F alpha, which is the same as alpha F in the case of regular old scalars and things like that. Okay? But I'm going to write it this way because it's important. Well, if I do that, okay, and if I have this gradient of this thing, well, if I got this gradient, if I multiply by some scalar, okay, a scalar function, f, well, then multiplying by a scalar, this just means del f, okay, which is not the same as f gradient. I mean, this is still an operator. It's still waiting for something, okay? But this is how you can kind of think about it. So that's a way of thinking about it. So the process of taking the gradient is like multiplying a vector by a scalar. Okay? What else can we do? Well, we can do a dot product. Okay? We can do a dot product. Suppose you have some f dot a or something like that, and you know how to do this. We can also do a cross product. F cross A. Okay? That's another nice way of thinking about it. This implies we might have some del dot F. This implies we might have some del cross F. Okay? Can we do these things? Well, here, this F here has got to be some vector field. It's got to be some function. But yes, it turns out we can. Okay? So let me start with a simpler one first. Let me start with this dot product thing. Okay? Suppose you got a vector field. Okay. F of, say, x, y, and z. What does this mean? This means that you got a vector, and at every point in space, there's some number that's associated with that vector. There's some x component of x, y, and z, I hat, plus some other function, some y component of x, y, and z, j hat, plus some third component of z of x, y, and z, k hat. Okay? That's what I mean by a vector field. And so depending on where you are, this thing can look differently. Okay? It can look different in different spots. Okay? So as an example, okay, f of x, y, and z is just, say, xi plus y, j plus z, k. What would this thing look like? Okay, well, if you plot this out. Okay. Actually, let me just take 2 dimensions because it's easier to draw on a 2-dimensional surface. Okay, so here's your x and y axes. What does this look like? Well, when x is 0, okay, when x is 0, then this just depends on y, and it points in the y direction. So it's a little bit here, more here, more here, and so on. Down this way, down this way, down that way. When y is 0, this just depends on x, and it gets bigger the further away you go. Now, when x and y are something, it points like this. Okay? And the further away you get, the bigger this thing gets. So this is your f. Okay, that's it, a vector field. So at every point in your space, this thing here gets, this thing here, okay, this vector field, has a certain direction and magnitude associated with it. So that's an example of that thing. Okay? So now what I can do is I can work out what's the dot product of del and f. Okay? Well, I think about this. It's not so bad. In fact, it's pretty easy. In fact, it's even easier than the gradient. Del dot f, okay, in general, is going to look like this. d dx, I hat plus d dy, j hat plus d dz, k hat, dotted into fx, I hat plus fy, j hat plus fz, k hat. Okay? Now, the dot product, remember, I dot I is equal to 1, I dot j is equal to 0, and so on, all 9 of those different conditions. Only if you have the same things do you get 1. If you got different things, you get 0. So of the 9 terms, 3 work out. And this means On the I dot I, this means derivative of fx with respect to x plus derivative of fy with respect to y plus derivative of fz with respect to z. That is my del dot f. And notice this is a scalar, as it has to be, right? The gradient is a vector. This vector field here is also a vector. A dot product takes two vectors and gives you a scalar. So you get this. All right? This thing here is the dot product. And so, as an example, let me take a more complicated example. So f of x, y, and z. Let me take this nice case. xi plus yj plus zk. A simple example. We'll do maybe a more complicated one here in a second. So del dot f is derivative of fx with respect to x plus derivative of fy with respect to y, df dz. Okay. Well, this is the derivative with respect to x of x. That's your x component. Okay. Your y component, d dy of y plus d dz of z. Okay. Well, dx is 1 plus 1 plus 1. You get 3. Okay. So notice this is the same as r. So what you find is del dot r, is not equal to 0, is equal to 3. Nothing to it. Piece of cake. See, it's even easier than the gradient because this thing here just has a, it's a scalar. There's no I, j, and k components. Okay, so that's an example. Something a little more complicated. Equals, what the heck, x squared yi plus z xj plus y squared zk, z cubed. Okay? So this tells me my f sub x is x squared y, my f sub y is zx, and my f z is y squared z cubed. Okay? So what's this del dot f? Well, it's derivative with respect to x of x squared y plus derivative with respect to y of zx plus derivative with respect to z of y squared. Okay, nothing to it. Here we go. 2xy plus 0. There's no y's here. Okay, there's z's and x's, but that's it. Plus 3y squared z squared. Okay, so del dot f in this case here is equal to 2xy plus 3y squared z. Okay, which again is a scalar. There's no I, j, and k hats here. Right? Okay. Now, let me show you something else very interesting. Okay. This, I found that this del dot f, well, del dot r was equal to 3. Okay. Is there also a way of doing this without having to worry about I, j, and k components? Because after all, I know that r in spherical coordinates in spherical coordinates, this thing is a little different. In spherical coordinates, r is just r hat. Is there a del dot r that I can work out? Can I use the gradient of this thing in spherical coordinates? Yes, the problem is it becomes more complicated. Okay? The problem is it's not quite as simple as you might expect. Okay? Why? Because you have to switch and redo the derivatives. Okay? For instance, well, I'll just kind of indicate how you go about doing this. Okay? You're working out dfx dx. Okay? I don't want to go too much into detail because, for one, it's already going long. Here's the thing, okay? Del dot f in Cartesian is exactly equal to del dot f in spherical coordinates. Why? Well, both sides are scalars. Both sides are not vectors. A scalar cannot depend on the coordinate system that you use to describe it. So this answer that you get has got to be the same in both cases. Okay? But the problem is that the vectors themselves, the vector components, are going to be different. And so it shouldn't be any surprise that because the f is different in Cartesian coordinates than it is in spherical coordinates, then the gradient operator should also be different. Okay? The problem is it's not quite as easy to work out as you might think. Okay? The del dot, you can't just sort of take the this thing here and apply it sort of as easily as you might expect. It turns out. Okay? And there's ways of proving this. I don't want to bother with it right now, unfortunately. Okay. What does it turn out to be in spherical? Okay. Del dot F, okay, in spherical comes out to be 1 over R ddr of R times F sub R. Okay. That's the first term. Okay. First term. Complicated. Sorry, can't help it. Okay. Can't help it. What's the next term? 1 over R sine theta dd theta sine theta f theta. Okay, that's the next term. Plus 1 over R sine theta df phi d phi. More complicated. So the question becomes, well, which one are you going to be more likely to use? Okay. Would you use spherical coordinates with all these extra pieces? Well, it's just derivative, so it's not actually that bad to figure out. Or should you use Cartesian coordinates? Well, it depends. In the case of Cartesian coordinates, okay, this was a little bit of work. Not so bad, a little bit of work. Okay? But in the case of spherical coordinates, okay, suppose I want del dot R in spherical coordinates. Okay, I know the answer, okay, and so that's nice. And I think I've even written it wrong. I think I've actually written it. This is wrong. Okay, sorry, it should be this, which means that the thing I write here is also going to be wrong. I'll fix it in a bit, though. Okay, so del dot R in spherical coordinates. Well, in spherical coordinates, my f here, well, this is just R vector, which is the same as R hat. So I don't have any theta hat or phi hat pieces. So in this case, my del dot F is real easy. It's just 1 over R squared ddr, where I can use a total derivative now, times R. Okay, it's just this piece. And this is 1 over R squared ddr of R cubed, which is 1 over R squared times 3R squared, which is 3. And so sure enough, del dot F is equal to 3. Okay? There you go. So it's not so bad. So in a lot of situations, we'll only have sort of purely radial pieces, so it's not all that much work, actually. It's just something you got to be a little bit more careful about with these extra little R squareds. Notice they don't cancel off. Okay? They're not going to cancel off. You got to worry about these things. Okay? So here are incorrectly written. Oh, no, I did have it right. I was looking at the wrong thing. Okay. So here are written expressions for what I'm calling the divergence, okay, this gradient dot F in these different coordinate systems. It's very easy in Cartesian coordinates. It's something you're easily able to memorize. But in the case of cylindrical or spherical coordinates, not so easy. Okay? But again, it's on this handy electrodynamics information sheet, so you never forget about it. Okay? So this is the dot product. But here's the very interesting thing. If you were able to express all of these things, this function here, this f, in terms of all the different things, different sets of variables with the different components and so on, you will get the same answer in every case. Notice that's what we did here. I worked it out in spherical coordinates, expressing this as a spherical coordinate thing. I worked it out in Cartesian coordinates, expressing it as a Cartesian coordinate thing. I get the same answer. That's always the case, okay? The divergence, what that means, I'll tell you in a second, is a scalar quantity. Okay? So it does not depend on coordinates. Okay? So no matter how you choose to work it out, you will always get the same answer. Okay? It's just some are a little bit more work than others. Okay? Now, what do I mean by divergence? Well, look at what this thing is measuring. This measures how fast your function changes in the x direction, plus how fast it changes in the y, plus how fast it changes in the z direction. Okay? So if you've got a situation here, here's one. Okay? Here's this. This is basically r. Okay? It's just r looked at along the z direction. Look at what this thing is doing. Look at how, when you calculate the divergence of this thing, you got a number. If this is it, you just get 2. Okay? So for this situation here, your del dot f would be equal to 2. But it's a positive number. What if you flip the sign of this thing? What if you flip the x goes to minus x and y goes to minus y? Well, in that case, your vector field would just all point in. It would look kind of like a gravitational field. Your del dot f in that case would be minus 2. That's how much something sort of spreads out. Okay, that's kind of interesting. Let me look at another sort of thing here. Okay, suppose I work out some other thing. Suppose, as another example, I work out f of xy. Okay, let me again just take a 2D case because it's easy to draw. How about minus y I hat plus x j hat? What would this look like? Well, again, you kind of look at the directions. Okay, when x is 0, so all along the 0 direction, the y. Okay, so you look along x equals 0, so that's along the y-axis. The further up you go, the bigger y gets, and so the bigger your arrows are going to get. Okay, so it starts off very small. The minus sign comes because it's pointing backwards, and so on. Down here, it's going to point in this direction. Okay, when when y is 0, but x is positive, points like this, and so on. And then it, on the other hand, goes like this. And so this vector field here, I think you can kind of see, it swirls around. Okay? Let me work out the divergence of this thing. Would be derivative with respect to x of minus y plus derivative with respect to y of x, and that's 0. So in this case, when it's swirling around, okay, del dot f equals 0. And so that's how we can think about it. Okay? When something's spreading out here, this is positive. You get a positive divergence. That's what this thing is called. You get a positive divergence when something is spreading out. When something is swirling around, you get no divergence. That's how we think about this thing. Okay? So this thing here represents, say, a positive divergence of your thing, okay? Of your vector field. And so the divergence, and this is really the best way of thinking about it, and you can remember it from the name, the divergence. This is a measure of how much something spreads out. Okay? Measure of how much something spreads out. If something spreads out, it's got a positive divergence. So something that looks like this has del dot f bigger than 0. What if it heads in? Then del dot f is less than 0. If it swirls around like this, del dot f is equal to 0. Okay? Nothing to it. Piece of cake. Okay? So again, I've got the divergences listed in different coordinate systems. You can calculate all kinds of nice things. Okay? And here's a nice geometric picture for what that is. All right. So that's the dot product. What was the other thing we could do? A cross product. All right, this is a little tougher. Cross product. Okay. Let me just remind you how you calculate the cross product of two vectors. If you got A as your AX, I hat, plus ay j hat plus az k hat. And b is bx I hat plus by j hat plus bz k hat. Well, there's different ways you can do this. Okay, you can sort of remember it, or you can remember I cross I. Well, I cross I is 0, I cross j is k, and so on from this right-hand rule and so on. You can also remember it in terms of a determinant. I, j, k, ax, ay, az, bx. AYBZ minus AZBY I hat plus AZBX minus AXBZ J hat. You say, hi, you missed a sign. No, I didn't. I moved it this way, okay, for a reason. This is correct. Plus AXBY. Oops. AYBX K hat. Yes, I know when you do a determinant, you change the sign of the second thing. I move the things inside around so that it doesn't mess up. Why? Well, look at the order. I got Y, Z, X, Z, X, Y, Z, X, Y, Y, Z, X, and it flips. It's a nice cyclic permutation, so it's an easy way to remember these things. Okay, so this is your A cross B. You can also think about it as magnitude A, magnitude B times the sine of the angle, but we actually won't use that. Okay, so with this in mind, now I can start asking about, well, what is del cross F? Okay, how do I define that? Well, I define it in the same way. Okay, what this word means, the curl, we'll see in a minute. So, del cross F. Well, what's that? Well, this is the same as your ddx I plus ddy j plus ddz k cross your fxi plus fyj plus fzk. Okay? So again, we can think about this in terms of a determinant. I, j, k, derivative with respect to x, derivative with respect to y, derivative with respect to z, fx, fy, fz. So again, this is a vector. Okay? It's a vector. A cross product takes two vectors and gives you another vector, which is perpendicular to both of them. That's kind of interesting. We'll think about that in a bit. Okay? This is the same as dfz dy minus dfy dz I hat plus df, again, I'm not messing up a sign, x dz minus dfz dx j hat plus df y dx minus dfx dy k hat. That is my cross product of my gradient with my function. Okay? How do I interpret this? Well, we'll get there in a second. Okay? Let's do a couple of interesting examples. Okay? So, two examples. How about f is r? Whoops. Well, I haven't told you what this thing is in spherical coordinates. Okay, I'll show you. It's a mess. Excuse me, I gotta sneeze. Allergies, sorry. By the way, if you hear me sort of sniffling and sneezing, it's not a cold, it's allergies. So let's work this thing out. Okay, so del cross F is equal to what? All right, so this is, again, d f z dy minus dfy dz I hat plus df, yeah, it's a mess, sometimes that happens, dz minus dfz dy j hat plus dfy dx minus dfx dy k hat. Okay, here we go. And so, first term, dfz dy. Okay? Well, there's no thing, that's 0. dfy dz. Well, y and z are two different things. That's 0. I hat. All right, that's easy. Okay. dfx. Okay. Well, there's my x component. It's x. It's not z, so that's 0. dfz dy, 0. J plus dfy dx, 0. Minus 0. K hat. So this is 0. So in other words, del cross r is equal to 0. I'll remind you that del dot r was equal to 3. Okay, so you worked out your first cross product of your gradient operator with the radial position vector. Okay, nice. Okay, well, how about one more? Okay, let's take that other nice example. F was minus y I hat plus x j hat. Okay, so if you like, plus 0 k hat. Okay. So here we go. Del cross F is equal to partial f z partial y minus dfy dz I hat plus dfx dz minus df. Once you sort of get the pattern, you can just write this thing down. It's not hard to remember. You just got to remember how it starts. dfz dx j hat plus dfy dx minus dfx dy k hat. What do we got? So dfz dy, there's no z component, that's 0. Minus the y component with respect to z, well, the y component is x, that's 0. Plus the x component with respect to z, that's 0. There's no z's here at all. Minus the z component, that's 0. J hat. Looks like it's almost 0. Derivative of the y component with respect to x, that's a 1. Okay, the y component here is x, so its derivative is just 1. Minus derivative of the x component with respect to y, minus 1. K hat. And so you get 2 k hat. So you find in this case, del cross F is equal to 2 k hat. It's a vector. Notice it's a vector which is perpendicular to both, to F here, okay? And it's going to be perpendicular in another sense to the gradient operator. We'll talk about that. And I'll remind you again that del dot F was equal to 0. Okay? So that's kind of neat. This is kind of interesting. And so think about, how do we interpret this? Okay, how do we think about this? Okay, well, in this situation here, remember we had something that was swirling around. Okay, it's got no divergence, but it's got this cross product thing. In this case back here, we had something that was spreading out, but it wasn't swirling around. So it had a non-zero divergence, but it's got this 0 cross product. So how do we think about these things? Well, when you've got these things here which are swirling around like this, okay, here, because it's swirling around, the divergence is 0. Okay, it's swirling, it's not spreading. On the other hand, this cross product here, this del cross F, would not be 0. And depending on the direction in which it circulates around, you might get positive or negative. Okay? In this case, because it's circulating in this direction, it's a right-hand rule. Because it's circulating in this direction, this points out. Okay? This del cross F. Okay? If it circled the other way, okay, if I change the sign on these things, it would point in. It would be minus 2k. All right? And so that tells you something very interesting. So in this case, it would point in. Okay? In this case, it would point out. And so that's what we get. Okay? So in this situation here, when your divergence is 0, because it's swirling around, this del cross F, what's called the curl of F, is non-zero. And so if the divergence measures how much something spreads out, the curl measures how much something spins around. Okay? Or how much it circulates. Okay? And so circulation. So if you've got water swirling around in a whirlpool, or if it's going down the drain, that's actually bad. If it's just swirling around, it's got a non-zero curl, but it's got a zero divergence. If the water is spraying out of a hose, directly straight out, it would have a non-zero divergence, but a zero curl. Okay? In general, you can have sort of both. Okay? So that's it. Okay? Now, am I going to show you the thing in other coordinate systems? Of course. Okay? Here's what it is in other coordinate systems. It's a mess. Yeah, the curl is the nasty one. The curl is the one I remember in Cartesian coordinates. I don't remember in the rest. I always got to look it up. Okay. I do remember the divergence and a couple of other things in spherical because I use them so much. Curl doesn't come up quite as often. Okay. There's ways of working it out, but I'm not going to bother you with them. All right. So, nothing to it. So, we've got our different things here. Okay. So, again, we've got our gradient. Okay. Del F. This is a vector. Okay. We've got our divergence. Del dot F. This is a scalar. Okay. And we've got our cross product. Okay, our curl. This is a vector. And if you read the Feynman lectures on physics, which I really do recommend, I hope you do, there's a slight difference between the different kinds of vectors. Okay, the curl is actually what's called a pseudo vector because it changes sign if you look at it in a mirror. Okay? It's things we're not going to worry about, but it's just kind of an interesting sort of thing. Okay, so this is as far as we can go with first derivatives. But why stop there? Okay, can we go to second derivatives? Absolutely. Okay, can I apply these gradient things again? Yes, I can. Okay, and there's all kinds of nice ways that we can apply these things. Okay, we're getting close to the end, by the way, so don't worry so much. Okay, apply, act with gradient again. Okay, so what can we do? What are some other things that we can do? Some other sort of vector identities. Okay? Well, we've got a vector here. Okay? Del F. Okay? What can we do? Okay? Well, this thing here is a vector, so what can I do with a vector? Well, I can do del dot del F, or I can do del cross del F. Those are the only two choices that I can have. Okay? I can't do the gradient of the gradient because the gradient is already a vector. I'm supposed to act with the gradient on a scalar. So that's it. Okay, so this is the only two things I can do with this. With the divergence, the only thing I can do is take the gradient of that divergence. Okay, that's it. I can't do anything else because this is a scalar. The only thing that gives me the only thing I can do with a scalar is take the gradient of it. Okay? And then in the case of the curl, what can I do there? Well, since it's a vector, I can do the same things. Del dot del cross F or del cross F. Okay, so these are my only choices. So let's talk about each one. Okay, some of these are actually zero, which is very nice. Okay, del dot del F. What's this? Well, you just work it out. Okay, in Cartesian coordinates. Notice this is going to be a scalar. It's the dot product of two vectors. Whoops, why? Dotted into df dx I plus df dy j plus df dz k. Well, again, the dot product gets rid of most of these things, gets rid of 6 of the 9 possible sort of choices, and I just have this thing acting on that thing. This gives me the second derivative of f with respect to x, plus the second derivative of f with respect to y, plus the second derivative of f with respect to z. Okay? And that's what you get. So this is del dot del f. This combination shows up all the time. It's got its own nice little notation. This thing is defined as del squared f. Sometimes you'll see it as delta f. I don't like that notation personally. This thing here is what's called the Laplacian. Okay? Okay? The Laplacian is that combination of things. Okay? And it's a very, very important equation, and one we're going to see a whole bunch throughout the semester. Okay? So this is the Laplacian. So there you go. Okay? I think at this point there's no sense to really trying to calculate some examples. You can work out the partial derivatives just as easily as I can at this point. Okay? So I got that. Okay, so that's one. Good. Next. Del cross del F. What is this equal to? Okay. Well, you can work out the cross product here. This will be I, J, K, d dx, d dy, d dz, df dx, df dy, df dz. Okay. Let me just show you one little term here. This will be your I component. I'll just do the first one. This will be second derivative of f with respect to dy dz minus d squared f dz dy plus other terms. But this is the same. Remember, our second derivatives commute with each other. In other words, it doesn't matter what order you take. This will be 0. You can check that the rest are 0 also. So happily, del cross del f is equal to 0, no matter what the function is. So that's very nice. So this is a very, very useful identity. That's always true. Okay? It's always true. And in fact, this has a nice geometric picture. Remember, the gradient is the direction you move to change as rapidly as possible. The curl measures how much something's spinning around. Well, if you're moving from one spot to the next as fast as possible, you're probably going in a line. You're not curling around. So if you're curling, you're not heading in the right direction to change as fast as possible. So there's a nice geometric picture. Okay, so that's nice. Piece of cake. Okay? So that's that one. Okay, this is equal to 0. This one here, okay, I'll just write it out so you can kind of see what it is, because it's something that does show up from time to time. Okay. Gradient of del dot f. Well, that's just d dx of del dot f I plus d dy of del dot f j plus d dz of del dot f k. Okay. And so this is a big bunch of mess because this is a derivative with respect to x plus, well, d dx. I'll just write out a couple of terms of dfx dx plus dfy dy plus dfz dz I hat plus and so on. So it's just a big mess, and it doesn't simplify down to anything. Okay? All right. So that's what you get. Okay? Incidentally, there's one more thing that sometimes pops up, something like f dot del on f. And this looks mysterious, but you just work out the components. This would be fx partial x plus fy d dy plus fz d dz on f, which is the same as fx partial x plus fy df dy and so on. Okay, so again, just work out the components. It's not so bad once you got it. Okay, so I got that. Now I just have a couple more. Okay, this one here. Okay, del cross del, or del dot del cross f. Well, this is kind of like, well, remember, this thing here gives you something at right angles to both f and del cross f. Now you're dotting it with something along the direction of gradient. This turns out to be 0. Okay, again, this is just d dx of del cross f, the x component of this, plus d dy of del cross f, the y component of this thing, plus d dz of del cross f, the z component. And that's it. Okay. Now, again, just to kind of show you this, this piece here would be d f z dy minus dfy dz, d dx of this thing, plus d dy of df, I'm doing more than I was gonna, but just to show you, df z dx plus ddz of dfy dx minus dfx dz. Okay, that's what you get. Now look, this piece here, dfz dy, you got this piece over here. This is ddx ddy, but this is ddy dz. It doesn't matter. These cancel. So this cancels that. Okay. Next term, dy dz. Well, here you go. This cancels that. And then finally, this cancels that. So this is equal to 0. Okay? And so yes, so this is another nice identity. Del dot del cross f equals 0. Again, always true. And so it's a very, very handy, nice identity. And again, there's a nice geometric picture. Remember, the curl measures how much something is spinning around. The divergence measures how much something is spreading out. If it's spinning around, it's not spreading out. So the divergence of the curl is always 0. Piece of cake. Okay, nothing to it. So we got that. Okay. Last one. This is one that shows up from time to time. Okay. Oops, I did not want to do that. Okay. No, it doesn't want to go away. Oh, I'll just write underneath it. Del cross f is equal to what? Well, this is something you got to work out. It's a cross product of a cross product and so on. Okay. It turns out that there's a very useful identity. Okay? A cross B cross C. It's what's called back cab. Okay? Which you can also write this way. Okay, it's just as good because it's multiplying a scalar by a vector. So if you work this thing out here, you get that del cross f is equal to del of del dot f minus del dot del f, and that's it. Okay, so this is a very, very handy one, which again we'll use a lot. Okay, and so this is just a nice identity. Okay, and again, you can work out all the components, and I encourage you to try, sit down and do it once, because it does actually come out nice, and it is something which is very, very useful to actually know how to do, and it's good to sort of do it once. Okay, so that's all the vector identities. Okay, and now we're done with all the hard stuff. Okay, I just want to show you. Okay, yeah, the Laplacian, it looks more complicated in different coordinate systems. Okay, this is one that we'll use a bunch. In fact, this is one we might use more, the spherical coordinates, because in electricity and magnetism, things depend on spherical coordinates. Okay. In addition, I want to show you some of these useful vector identities. These are some, again, all written on that handy information sheet. Okay, but these are very, very useful things. Okay, notice there's this nice cyclic permutation sort of thing here. Okay, the A goes to the back, but then the B comes, and so on. Okay, very nice. Okay, some other things we talked about. Okay, more of these useful vector identities. Okay, what if you've got the product of a couple of functions and you take the gradient? Well, it's just the product rule, the Leibniz rule, if you want to get fancy. Okay, but a bunch of these kinds of things, again, all written down for you. Okay, so these are just some useful sorts of things which are handy to know, handy to sort of prove, and we'll use them from time to time. Okay. In addition, these other very nice vector identities, okay, divergence of the curl is 0, and curl of the gradient is 0. Incidentally, there's something called the Helmholtz theorem, which says that if you have some vector so that del dot, say, b is equal to 0, this implies it can always be written as the curl of some other vector. Okay? It follows directly from this, because if you take the divergence of both sides, you get 0. Also, the second one here, if you have some field E so that del cross E is equal to 0, this implies that you can write E as the gradient minus y minus, just because, of some other function. Okay? And so this follows directly from this rule. Okay, so very, very nice. Okay? And so we got all kinds of very nice sorts of things. Okay? So the last thing that I want to mention, okay, and this is where all the math is done here. Now it's sort of ideas. Okay? More math to come next time. What does all this have to do with the stuff we're going to be talking about? Okay? The laws of electricity and magnetism. Okay? So we're going to be talking, okay, we're going to be starting not quite next lecture, but the one after. We're going to start electricity, really electromagnetism, or electrodynamics. Okay, electromagnetism. Okay, or E&M is usually what people sort of say. Okay, E&M. Electricity and magnetism. We're going to be starting to talk about this kind of stuff. And so it turns out, okay, that the most convenient and best way of writing the equations of Maxwell, the equations of electricity and magnetism, is in terms of these gradient, divergence, and curl operators. They are the simplest thing. And by doing that, we can write everything in terms of 4 very simple equations. Okay? And so I just want to sort of motivate the equations by telling you what happens, okay? The ideas, okay? And how you sort of picture it, okay? There is an electric field. Okay? Electric fields can be created by charges in the same way that masses can create gravitational fields. And so if you have some charge around, then there's an electric field that radiates out from that charge. Okay? And so there's a divergence of the electric field. And the bigger the amount of charge that you have, electric charge that you have, like from protons, electrons, and things like that, the bigger amount of electric field you're going to have. So there's going to be a divergence of the field, which should be proportional to how much charge there is. Okay, that's it. How simple is that? In other words, you got a whole bunch of charge sitting here, then you're going to have bigger electric fields. If the charge is more concentrated, you have a bigger charge density, in other words. Okay, charge per unit volume. Then the bigger that charge per unit volume is, the bigger amount of electric field you're going to have. Piece of cake. If the charge density is negative, then the electric field just points the opposite direction. Nothing to it. Okay? That's one thing. Okay? In addition, there's a magnetic field. Okay? The magnetic field doesn't spread out. It forms closed loops. Okay? If you have a bar magnet, for instance, with a north pole and a south pole here, then this magnetic field spreads out and circles around. This is your B. Why B? Well, we'll talk about it later. Okay? If you have a wire carrying a current, an electric current, there's a magnetic field that circles around this thing. But it forms closed loop. It doesn't spread out. There is no, B doesn't diverge. Okay? So, no divergence. There's a curl, you can see, because it is swirling around, but it doesn't diverge. Okay? Here, in this case, the electric field, it looks like there shouldn't be a curl. However, it turns out that there's also another complication. So if that was it, okay, if electricity and magnetism was not related, that would kind of be it, sort of. But it turns out very interestingly. Okay? Fields, electric fields. Okay. Oh, and by the way, B doesn't diverge, but it can be produced by currents, by moving charges. And the bigger the electric current, the more amps you have, the bigger that magnetic field. Okay? In addition, the electric field can do something else very, very interesting. Okay? The electric field can be created. Okay? Can be created without charge by a changing magnetic field. Take a bar magnet, wiggle it around. You make electricity. You make an electric field. Okay? And the changing magnetic field, if you got a magnetic field that points in this direction, but it's changing, B, then we induce an electric field that circles around. The electric field circles around changing B. And the faster B changes, okay, sorry, this is getting a little messy. The faster B changes, the bigger the induced field. Okay? So that's very interesting. What that tells you is that electricity and magnetism are not really two separate things. By wiggling a magnet around, by changing a magnetic field, you can induce and create an electric field. Now you might wonder, is the opposite true? Okay? If we change the electric field, do we create magnetism? Yes. Yes, we do. And that's very, very, very interesting. Okay? So if I have a changing electric field, okay, so drawing red for the electric field, E is changing, then this induces a B, a magnetic field, that also circles around. In exactly the same way as it works here. And it's the same idea. The faster B is changing, the bigger the B you get. Okay? These are the ideas. These are the ideas. Everything else follows from here. Everything else is just sort of deduction. This is the physics. These are the ideas. And these things you can start to see. Look, a divergence of the electric field. Okay? You're going to be working out a del dot E. And that should be proportional to how much charge density there is, which I can write as this rho. And the proportionality constant I'm going to write as 1 over epsilon naught for mysterious reasons. Okay? This equation says exactly this. Okay? B doesn't diverge. Well, that just means that del dot B is equal to 0. Nothing to it. Forms closed loops, spins around. Okay? E circles around. That should make you think curl. Is the changing B. That should make you think derivative. Derivative with respect to time. Turns out there's a minus. And it's a partial derivative because B could depend on all kinds of things. Okay? B circles around. That should make you think curl. Now, there's two things that you can have. Remember, it can be produced by currents. Okay? Specifically what's called current densities, okay, which I'll write as J. That's how is the current sort of spread out over the area of the wire. Okay? It's proportional to it, so I'll call that constant mu naught times J. And if this wasn't true, that would be all there was. But we have to add on another proportionality bit times how fast E is changing. Okay? And so you get 4 equations that completely describe everything about electricity and magnetism. Mu naught and epsilon naught are numbers. That's it. These equations are the Maxwell equations. And I've written them up here. These are the 4 Maxwell equations. And these contain everything that there is having to do with electricity and magnetism, and in fact more, as we'll discuss. Everything about electric charges, static electricity, lightning, magnetic fields on the sun, motors, generators, electric current, and so on, and so much more are in these 4 equations. Very simple equations because now you know what the symbols mean. So they are not at all scary. Furthermore, okay, with these rules, the fact that del dot B is equal to 0 means I can write B as the curl of some other vector, which is called the vector potential. And then I'll let you figure this out. Okay? Then this other law here for the curl of E, when I combine these two equations here, I can get this other one here. Okay? Using the fact that the curl of the gradient is always 0, and using this idea here. Okay? And so these are the complete, and I honestly mean complete, laws of electricity and magnetism. If you go on to study upper division electricity and magnetism, or even graduate level electromagnetism, you will see exactly the same equations. All you will learn is just more complicated ways of solving the same problem. Okay? So it's all the same stuff. All the same stuff, just fancier problems. Right? So this is a complete, absolutely complete theory of electricity and magnetism, and we'll be getting into some good amount of details. But again, in order to really do it, you need to understand the symbols. But I hope now, you see the symbols aren't so scary. Okay? It's just a bunch of little partial derivatives, which are just as easy as regular derivatives. All right? And so this finishes off the differential calculus, vector calculus. Okay? That still leaves integral vector calculus. Okay? Will that be as scary? Well, we'll see. Okay? But that's what I'm going to say for next time. Sorry if this went a little bit long, but at least it's sort of finished. But again, I really do recommend have a look through the Feynman lectures. This stuff here, on all the differential stuff, that's chapter 2 of volume 2. The first chapter is all this discussions of this kind of stuff. Okay? These conceptual ideas. I very much recommend that you read that as well. Okay? Volume 2, Chapter 3 is the integral stuff, which is what we'll be talking about next time. We'll talk about line integrals, surface integrals, volume integrals, Gauss's theorem, and Stokes' theorem. Okay, so that's all next time. Okay. Incidentally, when we finally start our discussions of electromagnetism, we're going to start with sort of simpler things, which are consequences of these things. And I really want to stress, anything that I write down, which is not these, is only approximate. Anything I write down where, for instance, E is just minus gradient V without this dA dt piece, that's only an approximation. That's not true in general. Okay? These are the correct laws, and everything else follows from them. Okay? But again, getting ahead of myself. More to come later. But for now, study up some partial derivatives. Okay? See you next time.